Okay, so it's my pleasure to introduce the third speaker of the day, Claudio Meneses from the Christian Albrechts Universität zu Kiel. And he's talking about the hyperkähler geometry of moduli of parabolic Higgs bundles in genus 0. Claudio, please go ahead.
Thank you very much. And I want to start by thanking the organizers for this kind invitation to give a talk at this event. It's nice to feel that I am back in the continent where I was born and raised. So it's a pleasure for me to be giving a talk in this event. So I'm going to talk about several branches of work that I've been doing recently. Maybe the latest and most important one is at a very early stage, and it's partly in collaboration with Harmut Weiss from the University of Kiel as well. And needless to say, if you have any question at any moment, feel free to interrupt me. Let me just show you a quick plan for this talk. I'm going to talk about the parabolic Higgs bundles and what motivated this work on parabolic Higgs bundles. And then let's say the core of the talk will be talking about certain geometric models, which is, let's say, partly in progress. For these moduli spaces, and finally, the approach, let's say the way we plan to attack several questions on the hyperkähler structures for these moduli spaces. So, in some sense, the talk is more on the differential geometry side, but I mean there are let's say many aspects which are algebro-geometric that I hope you will find interesting. Let me just quickly recall what parabolic Higgs bundles are. I mean, I'm going to concentrate in the case when the base curve is just the Riemann sphere, and one starts with a holomorphic vector bundle whose rank I'm going to denote by R and whose degree I'm going to denote by D. And then one has to fix, I mean, given that we are working on the Riemann sphere, on the projective line, one has to fix n different points as part of the initial data for the problem. In this case, one has to take at least 3, maybe 4, depending on what the rank is. And well, parabolic structure is basically a way to enrich the holomorphic data associated to a vector bundle, given that vector bundles in the sphere a little bit boring, I would say rigid. There's a very natural way to enrich the problem. Let's say to add moduli parameters to the problem, which is to introduce flags at each one of the fibers in the points that we've marked. And well, for several technical reasons, these flags have to be weighted. And well, let's say we weight them with a certain real numbers, which satisfy, let's say, some certain natural bounds. They're real numbers, and let's say they're chosen in increasing order, and the bound between 0 and 1. Now, the multiplicity of this real number has to do with the fact that, in general, the flags are not necessarily assumed to be complete, but in most of the talk, I'm going to concentrate in the case of rank 2. So in that case, flag is either complete or trivial. So I mean, just it's important to remember this. And what is a parabolic Higgs field? The parabolic Higgs field is let's say, additional data, which in a sense, or let's say, at least at an intuitive level, helps us model in cotangent directions to this moduli problem that one can think of. So basically, a parabolic Higgs field is a meromorphic differential with, at most, simple poles at each one of the marked points, and taking values in the bundle of endomorphisms. So in some sense, it's just a generalization of a matrix value differential with simple poles at the marked points. And here's something very important. I'm going to assume that the residues at each one of these marked points are nilpotent, and then they are related to the parabolic structure by leaving the flags invariant. I mean, of course, these residues may vanish, but then we need to find a way to let's say, understand this this relationship as well in that case. And okay. Introducing the weights, the parabolic weights has the purpose of giving a notion of stability, slope stability, which leads to moduli spaces in general. I mean, one can construct moduli spaces of stable or semi-stable parabolic Higgs bundles, and if one lets, let's say, the parabolic Higgs field be just identically zero, then one has let's say, a special, very special submanifold, or let's say some variety inside those moduli spaces, which is just the classical moduli space of stable parabolic bundles. And I guess it goes back to Hitchin, maybe not in the setup of parabolic bundles, but let's say that all the essential ideas are basically contained in his work, which is the fact that these moduli spaces admit a hyperkähler structure. So this means that from a holomorphic perspective, we can think about them in many different ways. There's, let's say, a whole Riemann sphere of holomorphic structures that one can consider. But today I'm just going to focus in one holomorphic structure, and more precisely, in one Kähler structure. That is the Kähler structure that comes from, let's say, the holomorphic structure of the puncture Riemann sphere that one starts with. It's usually called the complex structure I, but here, I mean, since I'm just considering that one, I'm going to omit the index, and I'm going to denote the Kähler structure, the Kähler form, by capital omega. Something that it's, I guess, very important is that the geometry of these spaces, and this is, let's say, an extra complication, a subtlety of considering parabolic structures, is that the geometry of these spaces M and N depends on a weight polytope. See, a space where all these parabolic weights live, and well, in general, has a very interesting combinatorial structure, which is determined by a finite set of semi-stability walls. And important subtlety here is that it may happen that this moduli space N of stable parabolic bundles may very well be empty in some cases, and that there's a subpolytope that was, let's say, described by many people like Bauer, Blekal, Lebesgue, where the moduli space of stable parabolic bundles is non-empty. But in general, let's say, it is important to know or remember that moduli spaces of parabolic Higgs bundles always exist independently, let's say, as long as one does not go to the boundary of this weight polytope, W. And well, the thing is that if one removes the semi-stability walls in these polytopes, the result is a disjoint union of open chambers. And when one chooses, let's say, an open chamber and chooses weights on it, it turns out that semi-stability coincides with stability, and these moduli spaces are actually smooth complex manifold. And so there's a very rich and interesting birational geometry of these spaces, which has been studied by many people. I mean, here I'm just mentioning several from let's say, what is known of the birational geometry, which is going to play a role here in this talk. I guess that in genus 0, the beginning is the work of Bauer, and let's say that almost all these works concentrate in the case of the moduli space of stable parabolic bundles, but there's also a generalization by Tadeusz to the case of parabolic Higgs bundles. So let's say, in some sense, the birational geometry is well understood. And what is the motivation for this talk? Well, let me just recall that in analogy to what happens in moduli of Riemann surfaces, one can construct certain tautological line bundles, which are given simply by, let's say, understanding the data that let's say, a very stable parabolic bundle one associates in terms of the flag at a given mark point. And let's say, in analogy to what happens on moduli of Riemann surfaces, one can associate cohomology classes to these line bundles, which are the analogs of psi classes, and can be represented by explicit curvature forms that I'm going to denote omega ij. And something important to know is that these moduli spaces are stratified. You see, in the same way that the Lim-Mumford compactification of the moduli of Riemann surfaces is naturally stratified, this moduli spaces also have a natural stratification. And I mean, so first of all, one can consider just Harder-Narasimhan filtrations associated with the underlying vector bundles. But then one can refine it by stratifying the flag manifolds associated to each one of the mark points. Now, this is very subtle because it depends on the choice of open chamber. And in general, there's an open stratum in this stratification for the moduli space that I'm going to denote by N0. So in mathematical physics, there are certain theories called non-compact Weston-Novikov-Witten models, say that they are a variation, a slightly less studied version of the very well-known compact, let's say SUN or Weston-Novikov-Witten models associated to the compact Lie group. These are different but related. And in particular, I mean, the reason why they're relevant is because their semi-classical theory of these models is related to the geometry of the moduli space of stable parabolic bundles. And it exploits an analogy with the Liouville theory and the moduli of Riemann surface, so let's say of Mark puncture spheres. And one can define a function in terms of critical values of these functionals. And I just want to mention that, I mean, there's let's say, a recipe that comes from mathematical physics to construct, let's say, a function that plays the role of a Kähler potential for the Kähler structure of the moduli space with respect to a specific, very special linear combination of tautological one-one forms. Here, I just want to remark that these parameters, beta ij, are linear in parabolic weights. So in a sense, let's say, the cohomology class of the Kähler form, it's can be explicitly expressed in terms of this, let's say, algebraic tautological classes, or say, generalization of psi classes. And the dependence is actually explicit in terms of parabolic weights. And some remarks is that, in fact, in some sense, these results are not what one would want in full, because it could happen that for some open chambers, this open Zariski open set is a whole moduli space, but for other upper chambers is not. And if one wants to understand the global results that work for any open chambers, one needs to understand very well the stratification of the moduli space N. And of course, one could approach the problem of computation of symplectic volumes with the previous result by reducing it to a problem to the intersecting theory of these psi classes. And this would lead to, let's say, analogous to nebulous formulas to the Sobolev recursive formulas for the volumes of this the Lim-Mumford compactifications in the case of M0n. And I just want to remark that these volumes have been computed in general by Witten in the 90s. But here, I mean, there's another way to do it, which I guess is interesting because it's related to intersection theory of these special classes. And well, an extension of these results to the moduli space of stable parabolic Higgs bundles is possible. And this takes me to the third part of the talk, where I talk a little bit about what I call geometric models. I mean, I guess that the idea is that one wants to understand the previous results better, or let's say one would like to understand the previous points that I just remarked better. And this leads naturally to try to understand geometric models for these moduli spaces. And I mean, I guess, as I mentioned before, the basic idea is that vector bundles are already rigid, and this leads to some natural and simple models for Harder-Narasimhan strata for these moduli spaces. So for simplicity, I'm going to concentrate in the case of rank 2. So, I mean, I guess that we know that bundles are just isomorphic to a direct sum of line bundles, and I'm going to denote the difference of this coefficients by capital N. I mean, in general, it's just going to be an index that is going to parameterize Harder-Narasimhan strata. That's going to be the purpose. So I guess the way the geometric model is constructed, or the geometric model I want to consider is constructed, starts by going to the fiber of each one of the mark points, and then consider, say, a very simple object, which is just the cone of nilpotent endomorphisms in the fiber. And then one can just blow up this space and obtain a line bundle, which is just isomorphic to, say, the canonical bundle of the projectivization of the fiber. Why would one want to do that? Well, because, you see, the idea is that intuitively what we're doing here is modeling residues of parabolic Higgs fields, but one wants to do it in such a way that the parabolic structure is remembered. And the way one can do that, if the parabolic Higgs field residue vanishes, is by simply modeling the object in terms of a blow-up. So this is like a basic object for the model. And more generally, quasi-parabolic Higgs bundles on a given splitting type are going to be modeled by, first of all, a point in a codimension tree subvariety of the product of these blown up surfaces. And why do we have this codimension tree condition? Well, because we are thinking of these points as residues of a parabolic Higgs field, and then we know that they satisfy a constraint, right, given by, let's say, a generalization of the fact that the sum of residues of a meromorphic differential with simple poles that is matrix valued, the sum of the residues has to be equal to 0. And moreover, I mean, there's an extra data which comes to the fact that the splitting type may be, let's say, not necessarily generic, which is adding some data that comes in the form of just endomorphism value of differential on the sphere. And the basis for let's say, the construction of the model is the following lemma. One can observe, it's not difficult to verify, that in genus 0, a parabolic Higgs field leaves a line sum bundle invariant. So this is, let's say, what one needs to define the stability, if and only if the parabolic Higgs field is nilpotent. And in this case, since we're in rank 2, nilpotency is just equivalent to the fact that the determinant is equal to 0. So one can observe many things, but I just want to emphasize that if we consider an arbitrary parabolic Higgs field whose determinant is not 0, then let's say, any associated parabolic Higgs bundle to this parabolic Higgs field can never be unstable, cannot be destabilized, simply because it's not going to stabilize any subbundle. So this already leads to some space that I'm going to denote by pH, which is sublocus in the model space, which is determined by the condition that the determinant is different from 0. I mean, the model space is the space that I considered before, which is moot. I mean, this is something that one can verify explicitly. And again, I mean, what I'm doing here is simply modeling the space of parabolic Higgs bundles whose underlying parabolic Higgs field is not nilpotent. So we know that this locus is always going to be stable independently of any choice of parabolic weights. And the theorem is that one can verify that the group of projectivized automorphisms of the splitting acts very improperly on this space. And see, one can simply consider a forgetful projection to the space of parabolic structures, or say, the space of quasi-parabolic bundles, which is actually automorphism invariant. So then one can simply take the quotient of this space by the action of this group, and this leads to a model for let's say, the space, let's say, of the Harlan-Narasimhan stratum restricted to the case where parabolic Higgs fields are not equal to 0. So in a sense, we're modeling different strata in the complement of the nilpotent cone in the moduli space. And in the case when the bundle is evenly split, that is when the splitting is generic. I mean, I guess this is going to depend on the parity of the degree, but let's say if the degree is even, one has the splitting when the distance of splitting coefficients is 0. or if the degree is odd, one has the case when the distance between the splitting coefficients is 1. And then, so the idea is that one takes a quadratic differential, which is going to model the determinant of a parabolic Higgs field, and construct a range covering over a space that I am denoting just NBS, which is, I mean, I guess the subparaindex BS is supposed to be related to supposed to mean very stable. So basically, I mean, what one gets from this construction is a model for the Baubil-Narasimhan-Ramanan maps that, let's say, are associated to the Hitchin fibration in this case. So it's very well known that, I mean, I guess one has an integrable system structure in these moduli spaces, and one can parameterize the fibers of this integral system as certain Jacobians. And I mean, I guess what one gets here very naturally and very explicitly is actually a model for a branch covering over a space of, let's say, at least over every Harder-Narasimhan stratum in the generic case, for a space of very stable parabolic bundles. And well, and here, then one just needs to study what could happen otherwise, which is that one needs to study the case when bundles could be unstable, depending on choices of weights. And we know that all that is going to occur only in the inverse image of 0 under the determinant map for parabolic Higgs fields. So this space, that inverse of 0, is going to be a model for the birational geometry of these spaces, both M and N. Again, I'm constructing very explicit spaces in terms essentially of linear algebra. Well, you see, what's important is that in general, everything is going to be reduced to simply understanding the combinatorial structure of the weight polytopes. So in particular, I mean, one can write down the say combinatorial characterizations of the different open chambers in this weight polytope, and this way parameterize the different stable components in a very natural way for the different spaces in that inverse of 0, which happen to be smooth. But of course, we want to consider models for a moduli space, so we need to consider the fact that there's a natural action by automorphisms there that identifies equivalent objects. And you see, this theorem is much more technical, but I wanted to reduce it to a statement that could be written inside a simple slide, say in terms of just a couple of lines. So let me just say that the basic idea is that if one chooses an open chamber, then one can classify the different stable components in that inverse of 0. And again, the action of the group of projectivized automorphisms is free and proper. So one can really take an explicit quotient there. And one can parameterize explicitly the wall crossing among these different stable components by explicit combinatorial data associated to neighboring chambers. So basically, one needs to find a way to parameterize chambers that could be neighboring by a given semistability wall. And in terms of this data, one can really write down what wall crossing is going to be, at least inside a given Harder-Narasimhan stratum. And then this just leads to a final outstanding problem of how to understand the gluing of Harder-Narasimhan strata. Right? That's a little bit more complicated, that requires more than the linear algebra that I just mentioned. Let me just try to clarify what's going on with a very simple and classical example, which is the case of the so-called toy model. You see, in this case, there's no birational geometry, but there's a very simple picture of what these models are, or how these models are going to look like in the end, which is, let's say, just the classical picture of the toy model of this elliptic surface associated to the D4 configuration. So I'm considering, again, the case of rank 2 and the case of 4 punctures. The degree could be even or odd. And you see the nilpotent cone, which is going to be the quotient of, or let's say the gluing of all quotients of that inverse of 0 for all possible splitting types admitting stable objects, let's say stable parabolic Higgs bundles, is going to look like all these lines that are either vertical or horizontal, which intersect, let's say, this horizontal line, which is, let's say, the central sphere, called also the bottom of the nilpotent cone. And, well, you see in these vertical lines, in the vertical components of the nilpotent cone, there are some special points that I also mark with red, which are, let's say, points that are very special in the sense that they happen to be fixed by a natural C-star action that we can define in these moduli spaces by simply multiplying the parabolic Higgs field by an arbitrary non-zero complex number. So one can understand, one can try to explicitly understand the action of C-star, and it turns out that there are 5 different fixed point components, which are with those 4 points that I've marked there on the vertical components, plus the bottom of the nilpotent cone, the central sphere, which is, let's say, in some cases, the moduli space of stable parabolic bundles, but if we make a choice of parabolic weights where this moduli space does not exist, then the moduli space is replaced by something else. I mean, but in the end, the geometry of the nilpotent cone is always the same. And then here, these diagonal lines are the Hitch intersections of the moduli space, which, let's say, are neatly tied to these vertical components of the nilpotent cone that have a very simple and natural characterization in terms of the branch loci of, let's say, the product of an elliptic curve associated to the divisor of the 4 marked points in the Riemann sphere. And let's say, I mean, the map in the second component is just the map that sends a complex number, a non-zero complex numbers to its square. And it's supposed to model the let's say, the map sending a parabolic Higgs field to its determinant. So this is basically the idea. And in progress, of course, one would like to understand, which is a very natural question, how the combinatorial characterization of parametrization of the general C-star fixed point loci on these models is going to look like. And most importantly, I guess, how it's going to be related to these analogs of psi classes on the bottom of the nilpotent cone, right? So, I mean, it is possible to write down, in this case, it's maybe a little bit messy and cumbersome to write the details, but let me just say that it's possible to write down explicit divisors for this psi classes, and they're always related to let's say, the complement of the very stable locus on the moduli space of stable parabolic bundles, which is just the complement of the intersection of the bottom of the nilpotent cone and these vertical components. So in the end, this intersection of all the components in the nilpotent cone are, let's say, encoding the geometry and topology of these psi classes in the moduli space. So in a sense, to understand the moduli space of stable parabolic bundles, we need to understand the moduli space of stable parabolic Higgs bundles. And finally, I go to the last time of my talk because I don't have much time left. As I said, this is a work in progress with Harmut Weiss. And what we know is that in general, we have a Hitchin system for these moduli spaces, which gives a notion of infinity for the moduli space. This has been thoroughly studied recently, mostly by Matseos, Voboda, Weiss, and Witt after, let's say, physical motivation of Gayotto, Moore, and Knightsky, which basically sets up the question of understanding the asymptotic geometry of the Hitchin hyperkähler metric. More recently, Fredriksson, Matteo, Svoboda, and Weiss studied the case of the toy model, again, rank 2 and n equal to 4. And they prove that it's, let's say, from the point of view of say, gravitational instantons or gauge theory, what it's called a gravitational instanton of type AELG, that's just, let's say, a way the geometry at infinity for this hyperkähler metric looks like. And they are working on, let's say, Torelli theorems for this ALG gravitational instantons. Basically, I mean, understanding how this, let's say, geometry, hyperkähler geometry, can be encoded in terms of natural moduli parameters associated to parabolic weights. And let's say more general objects called weakly parabolic Higgs bundles. There's a parallel story of moduli spaces of hyperpolygons, which I think Stephen Ryan is going to talk about next week, which is also related to these moduli spaces, thanks to, I mean, we know thanks to the work of Godegno and Mandini. And I just want to mention that in this parallel story, Ryan and Weiss are also studying the hyperkähler geometry for this moduli of hyperpolygons, which is, let's say, related but different in the sense that it has a different type, at least, let's say, in the case n equal to 4, which is called ALE. It's a different, let's say, volume growth condition at infinity. But you see, all these things are related. And I guess what one would like to do, or what we would like to do, is to approach the problem of understanding the hyperkähler metric from the point of view of so-called Fick-Scalating extension. So in a sense, I mean, it's known since let's say, since starting from work from Calabi, I mean, from the article which introduced the notion of hyperkähler metrics, that in a sense, hyperkähler metrics in spaces that are, let's say, cotangent bundles or very similar to cotangent bundles, is encoded in the base of this cotangent bundle. So in a sense, the idea is that if we know the Kähler geometry or the Kähler structure of the moduli space of stable parabolic bundles, one can, with this method of Fick-Scalating, understand the extension to the cotangent bundle, which is a Zariski open set in the moduli space of stable parabolic Higgs bundles. Well, this problem, as I said, was originally considered by Calabi in the case of projective spaces. If one considers a simple example, let's say the simplest possible example one can think of, the case of CP1 with the Fubini-Studi metric, what results there, the hyperkähler metric that results there is the so-called Eguchi-Hanson metric or gravitational instanton, which happens to be of type ALE. You see, so what we see is that, in a sense, understanding the metric or the curvature properties and the moduli space of stable parabolic Higgs bundles, or let's say any other moduli space, really is going to determine how this hyperkähler extension is going to look like. And in this study, an nilpotent cone should play a central role. And of course, a preliminary aim will be to try to understand how the Witten formula for the volume, the symplectic volume, extends to all other reducible components of the nilpotent cone. This is something that Fredriksson, Matteo, Svoboda, and Weiss are already studying in this Torelli problem. And I mean, what they have found is that the asymptotic geometry constraints are some. But again, understanding what the volume for these different nilpotent cone components is actually a very interesting and probably complicated problem that one would like to attack. And I guess that this is the end of my talk. I think I'm in time, and thank you for your attention.
Thank you, Claudio. Are there any questions or comments for Claudio?
I have a quick question rather, Marcus, if that's okay.
Yes,
Yeah.
go ahead,
So,
Steve.
yeah, thanks, thanks, Claudio, for the really, really nice talk. It was very, very interesting. And I just have a quick question. You know, another toy model that one can consider is genus 1 with 1 puncture. This also gives a moduli space of parabolic Higgs bundles, which is, again, an algebraic surface. You know, just like the genus 0 with 4 punctures. And I'm just wondering if this is a case that you've thought about at all in terms of this asymptotic hyperkähler geometry.
You see, I don't remember the details exactly, but as far as I know, as far as I remember, one may think of that case as a special case of the sphere with 4 mark points by letting parabolic weights, 3 parabolic weights equal to 1/2. If difference of parabolic weights, sorry, not parabolic weights, but difference of parabolic weights to be equal to 1/2, and the other one is free. So in a sense, I mean, again, I don't remember the details, but I think that case is just a particular case of the toy model with arbitrary parabolic weights.
Okay, that's interesting. Yeah, I wasn't thinking about one of these as a special case of the other. I'm sort of used to thinking about the elliptic curve, the 1 punctured elliptic curve case as being just a sort of separate case. But that's interesting that somehow tuning the weights, you know, produces one from the other. So I'll think about that. I
mean, there's some work required, but I think that's the case. That's the case, yeah.
Okay, yeah, and I probably have other questions for you, but I know that, you know, with the transition from to the next talk, so I'll leave it there. But
sure.
you know, I'll find occasion to ask you other things.
Yeah,
so, anyway,
I mean,
thanks,
it would be great to talk. Yeah.
Yeah. No, thanks a lot.
Thank you, Steve. Are there other questions or comments?